Bismillahirrahmanirrahim. Wassalatu wassalamu ala rasulil amin wa ala alihi wa sahbihi ajma'in. Amma ba'd. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Yeah, we wanted to save most of our time today, so Jazakallah khair for inviting me to do this presentation. And Jazakallah everyone for joining here to know each other and share some of the knowledge that we have, and on that we can have some discussion as well. I will quickly go to the presentation so that we can save time, and many of us are joining from different parts of the world at different times, and I think we are also coming from a really different background. So I have a little challenge there because it's a little complex topic. So the approach that I am going to take is like I want to keep it very simple so that all of us can understand. So some of the things might not be that much interesting for some of us, but there will be sessions that will be interesting and new for many of us. So that is approach, but towards the end, if you have anything to clarify, yeah, we can discuss, and whatever I know, we can share. And also, I am sure within the attendees itself, yeah, there will be others who can add value as well. So looking for that, so please engage in discussions as well, inshallah. Okay, so let me put the presentation back. Is it visible?
Yes, we can see it.
Okay, okay. Okay, so so quickly, this is what we are going to cover. So we'll have some foundation. So just to get up to speed, right, what we are talking about and what are these chips. And there is a history and geography. So exactly, there is some history for that, and there is a geographical part of semiconductor industry. So we'll touch upon that and how it is impacting our life and some of the geopolitical issues. I think this is one of the major reason all of us are really interested to know this, right? So and what is going to happen in future. So as we know, it is there, a semiconductor or the chips, right? There are different words that we always use, but it is there everywhere already. So first thing, it is there in phones, cars, all the AI that we are talking about, and all every systems, every electronic advanced or non-advanced systems, they have these chips inside. We know till now it was a world of, or the entire system in the world was mostly driven, controlled by oil. So that's why we call it, it's a new oil of the digital age. And without them, actually, it's an actual fact. Without all these chips, right now, most of the advancements that we already made in the human life, we won't be able to continue that without support of semiconductors. So having said that, I just wanted to go to some of the history, right? So let me use the quickly, right? So what is really happening, or what has already happened? So most of the advancements that we are talking about in the chip industry, it's actually part of quantum physics, right? So so we know electricity, and then we know atoms, right? So and then electrons, so how they flow, right? So how they flow, and actually the way electricity flows and the electrons flows within these chips, it's entirely different. So because it's really minute, and the rules of their behavior, right, at that micro level is very different from the way, right, electricity flows or any other things flows. So that's why as and when we have more advancements in physics, right, we have more controllability on electrons, we can understand something like that, and then it actually guided to shape the semiconductor industry. So and 1947 was one of the major milestone in human history, because we invented transistor, right? You can consider it as a small switch, right, which you can turn and off, and then you can also amplify electrical signals using that. So on the right side, you'll see a picture. I don't know how many of you recognize this. So this is one of the earlier vacuum tube based. So this is the vacuum tube. So earlier, before transistor, we used to have these heating elements. It's like bulky with glass, which is very risky to use, and you can scale, right? So those kind of structures. So those were the major building block electronic circuit earlier before transistor. So, and it was bulky as you see here. So after 1947, things change, right? So you can, because this is very tiny and you can control the electron flow. So that changed the entire the way we look at things, right? How do you implement circuits? Everything changed. And then after that, we talk. When we have transistor, it was a basic element, and then when you have multiple transistors and other elements integrated together, that become an actual chip, right? So and chip has its own packaging challenges because you have to put multiple transistors in that, and you have to integrate multiple transistors within a chip. So I hope I gave the basic idea. And then now let us now compare what really has happened, right, in last let's say 50 to 60 years after 1947. So many of us might know this is actually the ENIAC. So you can see this in University of Pennsylvania in US even now. So this is one of the panel of for all the 4 panels. So it had actually 18,000 vacuum tubes, right? Like the one I showed you here. And it was actually it was a computer. It was for a US Army, okay, and 1,500 square feet. It was in a room of 1,500 square feet. It had 1,500 relays, 1,500 relays, and it has 1 lakh resistors, right? It was done to speed up some of the calculations that they want to do on bombs, actually. So, but that time itself, it was actually 2,400 times faster than human, right? So it was in around after 1950s, you can say, yeah, just before 1950s. So now, if you talk about, so the chip that we have right now in our pockets, right? So it has actually 15 billion transistors. Okay, I mean, in just one chip. And then actually it contains a lot of different processes. That's what I'm coming to right now. So how do you get this? So you're getting going from 18,000 vacuum tubes, which are very bulky, which will fit in a room, to 15 billion transistors, which are very, very tiny, which will fit in your pocket, right? And here, a lot of heat, a lot of power, a lot of problems in connectivity, maintenance, a lot of things, right? So it's costly here. But here it is, as we can see, yeah, it's very efficient, right? Power efficient, area efficient. It's very small. You can scale, etc. So now, how do you do that? So I just want to quickly touch upon how we are doing that, right? Actually, if you look at the chips, right, it's actually, you might have heard about, but there are different words here. So a semiconductor is something which is like a physics behind that. Then we have VLSI. VLSI means very, very large scale integration. It's actually very large scale integration of transistors. And then you might have also heard about silicon. So what is silicon? Silicon is one of the element, right? So it's actually coming from sand. So this is the base material to make chips, right? Or the semiconductor. It actually comes from the sand, and sand, we know, it's a second most abundant material available. But there is a lot of complexity involved, right? Um, from getting a sand and converting that to some material like this, right? Which like chocolate bars, you can tell, and then a lot of chemical process, and then which will purify it and then make to tube like this. It's called ingot, and then you slice it, so like this, right, into this round shape, and then that is actual that's actual base material. So this itself is a huge process, right? So to get to this, and then after that, you have to actually put your actual chip or the logic or the circuit on this substance. So why I mentioned this, because it's not just from moving from a vacuum to a transistor is not that easy. There are a lot of different process involved, lot of different mechanisms, tools, right, equipments, lot of things involved. It's a completely different industry altogether. Right. So, and now we are talking about, so once you get this substance, right, this round, you will see, mostly you'll see it in a round shape. on this you can have multiple chips actually. So this material that we call it wafer, right? Like the chocolate wafer. So this will be varying in different sizes. So bigger size is better, but there is also a challenge in making a bigger size of this because it is more brittle, right? And how do you make sure there is no impurity and things like that? So okay, so now what I'm coming to what I'm going to tell next is about lithography. So lithography is the process of printing small circuits on this. So just understand that on this wafer there will be hundreds of actual chips. So one wafer itself can potentially hold multiple depending on the final size of the chip. So now I just wanted to, I don't know if I'm going very fast. Let me know if I'm going too fast. Yeah. So, but I thought I will cover quickly few points, and then if there is anything we can clarify later. So now, if you look at the industry itself, right? So one thing is we don't have any vacuum tube. I mean, you still get it. You can still get them in Amazon, by the way, if you want to. But it's like a 7-year, right? But most of the chip industry, I mean, all of the chip, 99.99%, or even more than that, has converted to this, right? So, and how do you do that? So, let's say you might have heard about chips from Apple or Nvidia or maybe Qualcomm, right? Different companies, right? So this has a lot of details, this slide. So if you want to read, you can read. But I would like to cover a few things for the general awareness. So ideally, you can think of it as a 3-step process. So there are some pre-silicon. So silicon, I mean, I hope you understand by fabrication is actually the making of that actual silicon wafer, right, with lithography, right? So before that, you have to actually design the circuit. So that's what we call it pre-silicon. So this is called pre-silicon. This is actually the silicon, and then post-silicon, right? So in the case of pre-silicon, it's easy to understand. So there is a lot of specification architecture. There is a lot of coding involved. Then there is software firmware, and there is a lot of verification process. This actually takes almost 70% of the time, right, in the all chip production cycle. And there is a concept of physical design and then actual tape out, and then this goes to the foundry. Foundry means the place or the factory where the chip is actually even made, right? Basically the net list, right? That's what the technical term. Whatever you give the logical information, right, of the circuit is actually imprinted on the silicon wafer. So that is done in the fab or or the fabrication factory, right? So and then it comes out, right? And then we do a lot of testing on the chip, and then it goes to the final product. So for example, when you are using an iPhone, it has a lot of chips involved, and it has a very big costly very innovative chip developed by Apple, and which will be which they are manufacturing or fabricating in TSMC fab, right? TSMC is in Taiwan, as you know. And then it comes back, and then they put the actual product. It will itself sit in a PCB of multiple chips, and then they will have the end iPhone, something like that. So the same thing happens for every industry and every product. So you can talk about, let's say, cars. So there are multiple chips sitting inside a car. So it is getting manufactured or designed in multiple places, right? Or designed by multiple companies. And then it is getting fabricated or actually produced, right, at multiple fabs. And then it comes back to the company, let's say Tesla, for example. Then they integrate those chips, right, to the actual circuitry, something like that. So just to also give you an idea about how big is this industry actually right now. So S&P 500, the biggest 500 companies, right? It is worth almost 55 trillion, right? So out of that, 35% is tech companies, right? It involves software and other companies as well. But out of this 513 major 13 semiconductor companies are there in this 500, including Nvidia, Apple, Broadcom, Qualcomm, those kind of companies, right? And if you see, out of 500, only 13. But actually, Yeah, out of this 55, these 13 companies are controlling almost 12%. So that is the impact of these companies on the overall economy situation. Yeah. Anyone has anything to clarify at the moment before I go to the next step? Yeah, I don't want to be a technical field presentation as well. Yeah. Is it going good? I don't know. Yeah.
So far good. So far good.
Okay, so far good. Okay. Okay, so if you want, you can read through this. So there are these are all one of the. I mean, there are many companies, by the way, who are working pre-silicon, right? Who are very good at pre-silicon. They are very good at. Some are very good at fabrication. Some are very good at. I mean, after that, some are very good at the product. For example, right? For example, Tesla. So they mostly work on the product, right? So they depend on chips, and they also have in-house chips, right? But not end-to-end. But company like Apple, for example, so they have a lot of in-house actual chip design, but they don't do any fabrication. So okay, they depend on TSMC for the fabrication, but they have a product like iPhone, for example, or Mac. So for example, the company like Qualcomm, right? So they work on the pre-silicon. Okay, they get it manufactured in TSMC and Samsung, but they don't have a product. So they sell the chip to companies like, for example, Xiaomi, right, for phones, or maybe LG, or give the modem chip to Apple, for example, something like that. So these are all different areas. Okay, another one is Intel, for example. It's a entirely different company, or even Samsung, right? Samsung and Intel, so they have design, they have fabrication, they also have a product. Right? I mean, yeah, something like that. So it all depends. So there is it has its own advantages and disadvantages. That also you'll have to understand once we go to the next slides. Okay, so now I just wanted to pause for a moment and then tell you one thing. This is something that has helped overall, right? So whatever we see today, all the advancements, I mean, at least on semiconductor industry, if you see, I told about that. So almost 50 to 60 years of hard work, right, at different domains. But also, if you see the speed at which it is going, right, including the AI advancements and things like that, there is a lot of interaction from academia to the industry, right? So it's very fast, and a lot of focus is being there. So why I'm telling this, because I mean, we also need to think, at least for our next generation. So it's always good to spend time in research and then find new ideas and try different things, right? So we should motivate that. Okay, so now let's talk about the type of chips, right? So this also just to clarify something. So you might have seen something like this. So even if you open anything, right, any electronic device, you'll see a circuit board like this, right? This green color is normal in that way, and you'll see a lot of this black, big blocks, right? You'll see small blocks also. So I mean, all of this. It can be different components, but many of them will be actual chips. So all these are chips that you see, and the small ones are other passive elements like resistors and capacitors. But the point here is, if you look at a normal, normal, even if you open old phone, right? Let's say a 10-year before phone, you will see big chips like this, right? So many of them will be CPUs, right? Many of them will be GPUs. Even if you open a laptop, right, you'll see this. You'll see memories and things like that. So what has happened over years is, earlier what happened, so here you can say this is CPU, this is GPU, something like that, and then you'll have to connect them through the PCB, right? But what is happening right now? So it is another example, right? What this is 2019 855 chip by Qualcomm, right? This is the front face, and this is the back of it. So whatever you see in white dots, it's actually the pin of the chip. So now between this one and this one, what is happening is, I mean, I don't know, this is a small picture, but whatever you see here, I mean, these are some of the small examples, but whatever you have, so it may be USB, it may be a modem, it may be a processor, it may be a GPU, it may be a camera module, it may be a video processing engine, it may be something that you are supporting on Wi-Fi, anything like that. So we have methodologies which will integrate all of this together. So that's what the concept of SoC. So I just wanted to introduce that name because you will see this. So there are companies that do SoCs like Apple, Intel, or Qualcomm. They can do at very big scale, right? But there are companies who still rely on this kind of integrations and a product like that. So it all depends on the industry and the final product. So if you want to really go to a small form factor with a very good control on area and power of your final product, you have to go to this. So now I think what we are going to do now is, but how complex it is. So let's try to understand what is the complexity of doing this, integrating a lot of different things. Okay, you can think about as your smartphone, right? And then all the functionalities that you can do with a smartphone, and then how all those functionalities, most of those functionalities are integrated into a single chip, right? Like this, right? So just a comparison. So in 2019, I will come to this technical term. It's called technical node or tech node. So which is using a 7 nanometer tech node or technology you can say. So it is actually containing 7.5 billion transistors. Okay, in a 73 mm square. This is actually 73 mm square. Within 73 mm square area, you have this many transistors, right? And once you fast forward to today, right, we are normally using 3 nanometer. So all the advanced chips from Qualcomm and Apple, for example, or even Intel, right, they have 19 billion. So almost 3 times, right, from 2019 to 2025, almost 6 years. In 6 years, we have almost 3 times or maybe 5, 2 to 3 times more transistors. So what is the meaning of more transistors? That means more logic. More logic means more functionalities, more accuracy, and whatever you want to do more, right? So you can implement more with the same kind of area, right? So that is a complexity that it is that has been achieved right now. But how do you do that? Okay, so before going there, so let's understand the tech node, right? So what we are talking about. So I just mentioned about 7 nanometer and 3 nanometer, right? But what is this, right? So I think the best way to understand is using our human hair, right? Look at your head and then look at your hair, one hair, right? So one hair is normally, if you take, it depends on the person also, maybe 100 micrometer, right? 1 micrometer is 1000 nanometer. So I don't think we can imagine something below that. It's very difficult to see also using eye, right? I mean, you can still see. I mean, there are things that you can still make below this, right? And you can see. But this just to relate easily. So what has happened? So 2004, it is called 90 nanometer. So 90 nanometer means the actual transistor. We talked about transistor. So initially we started with the hundreds of nanometers, right? And then when it was initially created, invented, then the size of the transistor itself went down, right, to 90 nanometer. So 90 nanometer means almost, I mean, one hair is actually 1000 times, okay, bigger than a transistor in 2004. You can think about it like that. Hair itself is 1000 times bigger than a transistor. Okay, so now, and you fast forward to here, right? We talk about 3 nanometer. So it's not, so earlier it was actually the actual size of the transistor, but there are a lot of other complexities. Now what happens is, okay, you have the transistor, that is the logic element, and you have to connect them. So it's not actually, the 3 nanometer is not the actual size of the transistor. The actual size of the transistor is almost 12 to 15 nanometer. Okay, so even if you take the upper bound 15 nanometer, it's actually, our human hair is 6,000 times bigger than the transistor. Okay, I don't know if how we can imagine that. So we can't see it actually. So it's very tiny like that. Okay, and this means that in a millimeter square area of a chip on a silicon wafer, you will have 225 million transistors. Okay, so it's very difficult to imagine all this, but we cannot tell that it's very big. And what happens is, what has happened over the years, last let's say 20 years specifically, the power consumed by the chip eventually has go down. So you can just easily understand this. Let's think about what happened, how we were using the smartphone like 10 years before. So when you play a video, it was it was heating, it was getting heated, and then after maybe 10-15 minutes you have to switch off, right? And power also was going down, right? And at the same time, performance, right? So the video that you used to see, or the recording that you do on the camera, right, or the Wi-Fi, it was very slow. It had a lot of issues, right? So it was actually a problem with the performance. But now, and also now it is supporting a lot of features, right? With the same price point, or relatively a smaller hike on the price point. So how do we achieve that? That is because we are doing this. We have done this innovation, right? So it's actually whatever we are using now, or whatever we are enjoying now, right, in our daily life. It's direct impact of the technology advancements that we have made in the last 10-20 years of time. That's what I wanted to conclude on this slide. Okay, so I just wanted to, from this slide, what we wanted to understand is it's really complex. The manufacturing or the conversion of a logical circuit, right, to an actual chip on the silicon wafer in a fab, right, using the method of lithography is very complex. Okay, so now this is so what has also happened in last 10 years especially, right? So we have a lot of high performance computing requirements right now, like data centers or all the AI related. Let's say when you're chatting with the ChatGPT, right, or when you're using any LLMs, right, they're actually running on chips, right? They're not running on a software, they're actually running on an actual hardware. Okay, and then we have a lot of personal computers and laptops, a very big industry. Then we have wireless communication like mobiles and all the other towers and things like that, right? A lot of traction on automotive. Automotive is actually is a really new area, I would say. I mean, there are chips in automotive, but all the advancements that we have made on other domains, it's going to come in automotive. That's what it's going to happen in next 5 to 10 years. And then we know consumer electronics. The thing with consumer electronics is like they are mostly working around this tech node, 90 nanometer, 45 nanometer, or maybe even above that, right? So it's not that complex, but those are the ones those initiated this process initially, and then mostly after this it was initiated by it was sorry, one second. It was driven by a smartphone, we can say. Now it is mostly driven by AI and all the new workloads, right? Okay. So now consumer electronics is still one of the bigger, if you look at the number of volume, right, it's very, very big. So all your microwave or AC or anything, fridge or any device, right, or even car, right? So there are a lot of things. And industrial electronics like robotics, for example, it's coming up. This is also one of the evolving area. I mean, we already have a lot of chips there, but we are going to automate a lot of things. And you can see there will be a lot of culmination, right, and cooperation among all these industries in near future, right? So, okay, so now let's talk about, I have, I think, 1 or 2 slides, maybe 3-4 slides, okay? So let's talk about how this is impacting the geopolitics, right? So we know that since it is getting used across everything, right? So defense is one thing, space is another thing, right? We know now Amazon also has satellites, right? And Tesla, I mean, not Tesla, he's also putting, Musk is also putting a lot of satellites. All the advanced machinery, arms, right, aeroplanes, everything, right? Most of them are destructive, right? We know, yeah, that's another thing. Most of these advancements are driven by military, right? That's a fact. But countries wanted to maintain that dominance, right? In name of, in terms of security or it is also a very big business, right? Yeah. If you can create chips to control your AI, 5G, defense, space, you are going to control the future, right? So that's a reality. We know USA and China and so many other countries like Japan, Taiwan, right? Etc. Right? So those countries are um, really controlling this all these tools and methodologies and the way we fabricate chips, right? So I just wanted to go back to this slide again. So we talked about this pre-silicon, and then this is the silicon manufacturing, and this is the actual product, right? So right now at the moment, right, the main focus is on this area, the fabrication, right? Because we have a lot of bottlenecks there. There is a lot of monopoly there, right, to go to the advanced nodes and advanced chips. And if you want to support high performance requirements, you need really cutting edge technologies. Okay, so at the moment, if you look at the high tech, TSMC, Samsung, Intel, right, mostly they have the high technologies, right, and within that TSMC has a very good edge. Just wanted to compare, so Canon and Nikon, right? So they are Japanese companies. So they were dominating, right, in last, I mean, another 20 years back. They were dominating. But they lost their domination because they didn't work on they don't have solutions for very high performance tech nodes, which are very reliable, right? So and at the same time, there is company like ASML, which is a Netherlands company. They can, this is the process company, right? But the actual devices, right, to use in a fab, it is actually manufactured by, for example, ASML. So ASML has, let's say, 3 nanometer to produce a 3 nanometer chip with a very good quality without, for mass production, only ASML has at the moment, right? Other companies also has, but they don't have I mean, they can't do that at scale, right? So that is the dependency and monopoly at the moment, right? That is causing issues around the world, right? That is the context. Now, what is happening is, I talked about advanced manufacturing. Anyone type something? Okay. Okay, so advanced manufacturing means, let's look about, okay, we talked about the transistors, but how are we going to do that, right? So there's a concept called, there are multiple technologies, but this is one of the famous technology right now. So EUV, we call it extreme ultraviolet. So basically, this is the methodology of printing as a logic circuit on that silicon wafer using a machine, right? Just think about like that. So it uses 13.5 nanometer laser light kind of thing, and not laser, I mean ultraviolet light. You can compare it like earlier, it was like 193 nanometer. So it's like very narrow, you can say. And also to put in perspective, like what is the effort they put, right? Okay, we tell they have monopoly. It took almost 17 years. So they started in 1990. So the 3 nanometer process that we are using right now, let's say available in an iPhone, right? So ASML developed that initially in 1990. They took almost 10 years to stabilize that, right? And then last 7 years, they are able to use it for mass production, something like that. Not only that, it involves a lot of precision lasers, it has ultra smooth mirrors, and it has a lot of vacuum change. It's a very big, very big complex, another physical, I mean physics, right? Area of physics and chemistry, right? So what they have done is, I think I'm getting some noise. Okay, sorry. Yeah. So one more thing. So what happened, right? If you see after the globalization, right, it helped them because they also have a lot of supply chain. So if you look at the actual lithography machine, right, it has almost 10,000 parts. Right? If you can put it in that simple way, it'll be more than that. But if you look at roughly 10,000 parts, so they are sourcing it, different materials and different parts from different other suppliers, right? And eventually they are integrating that. So they only have the actual recipe, right, to do that lithography machine. At the same time, they have the different supply chains which are spread across multiple parts of the world. So that's how they have developed it, and only they have it. And so what happens is whoever has direct control over ASML, they can control the sales, right, of these lithography machines to other companies, right? So there is a consortium of USA, Netherlands, Japan, Taiwan, and Korea, because Samsung also uses the same ASML machines. Intel also uses that. ASML machines. TSMC uses ASML. Okay, all of them are using the ASML lithography machines. And if you can control over that, you got the control. So it's very simple that way. Actually, it's very clear what they're doing and what they want to do. At the same time, one more thing. So I just wanted to go back to the same slide. If you look at this pre-silicon, so there is also some domination. So that's what I mentioned here. So there are a lot of tools and development flows that are involved, right, in this step, right, which are also a kind of a monopoly. So you will see three main companies, right, Synopsys, Cadence, and Siemens, right, which are controlling those softwares. So for example, what that means is, let's say you want to design something, right, write something, some actual code, right, of the RTL or the actual chip, right, using these Verilog and VHDL languages, and then you want to simulate that, right, before going for production. You have to depend on these tools for that. So because these are the you can think about, we talked about billion transistors. So these companies will help you to simulate that, right, on a software before going for a production, because you can do fixes and lot of trials, right, before going for production. Once you produce it, you can't change it. It's very difficult to change. I mean, you can't change it. Yeah, it's a bug, right, on the silicon, which is permanent. So that's why that control is also within this, right, within this mostly within this group of countries, you can say. And then what is happening within China, right? So it is very difficult for them to replace, because if someone blocks them with all this access, right, they can do it. So what I mean, roughly we can say that they are still behind 5 to 10 years behind of all these leading chips, right, that this group of countries are generating. They have a company called SMEE, a Shanghai machine, I think something. Yeah, it's a kind of a consortium owned by government. So they're trying to push it, right? Right now they could achieve only 28 nanometer. Now we are talking about 3 nanometer, right? So they are slightly behind, but they will push it. They won't leave it, right? So right now they are focusing on domestic needs. So what happens is everyone wants to secure manufacturing. That's what it is happening, right? Everyone wants to secure manufacturing of all the chips, because otherwise you won't even. So for example, China in last year, they actually imported, I mean, they spend money on importing chips than on oil. Okay, let me reiterate. Spending time on money on chips, right, in China this year is more than the amount they spend on importing oil. So that means they have a lot of products for that they need chips, right? So that they are not entirely manufacturing there. A lot of chips are coming from outside. So they wanted to at least, even on higher tech nodes, right? If some countries tell them that, okay, we want to give you chips, they won't be able to produce the final product. So that's why they're worried, and so that's why they are still working on the higher tech nodes, and later maybe they will come down and then secure their own manufacturing. There is also another side. So all this, we didn't talk about that, but there are a lot of basic materials, right? So if you look at in all of our advanced devices that we are using, it may be phone, it may be a laptop or car, right, or anything like that. So there are a lot of rare elements, right? Like for example, there are 17 rare elements which are used across magnets, right? So all of our phone has magnets, camera lens, display screens, actual lithography equipment. So we talked about ASML. So they need some of these rare elements, right? So what is happening right now is China controls that, right? They have the mining, big mines, and they also do the refining process. So let's say you have mines, right, in South America somewhere, right? It has to be refined, right, and converted to a final element, right? That is done in China. So almost 90%, 80% to 90%, they are doing 60 to 70% actual mines are there in China itself. So if they tell, okay, we want to supply something to ASML, ASML can do that. But the thing is actually these rare mining, I mean elements mines and processes, it can be built, right? So the complexity of this rare earth element management and compared to the advanced manufacturing, this has an edge. So, okay, that's a fact at the moment. Okay, let me repeat that. So the basic elements, right, and the process to get the elements, you can build it maybe 5 years, 10 years. You can also build this, but compared to this is more challenging. Okay. So what is happening is both of these country, I mean, group of countries, they're trying to restrict each other, right? That is one thing, and at the same time, both of them are trying to see alternate paths, right? So yeah, so that's what it is happening. Okay, so let me finish in 1 or 2. Okay, maybe 1 or 2 minutes. So then we can go to the reflections, and if you have any comments, you can do that. So what is happening is we see that because of this, a lot of focus is on actually building fabs, right? So you can think about fabs as big hospitals, which are very clean, right? But at the same time, the main problem is setting up the, you need to have the proper technologies to set up that, right? It's a big factory. But at the same time, it's a lot of cost to maintain that as well. And also a lot of, it's like even to work there, the workers there, you can't replace. I mean, it has a lot of, let's say Taiwan, for example, the TSMC, people working there, they are working in a very complex a niche area, right? So training people on that itself is a huge task, right? So, but I mean, countries are running behind that. They're setting up their own fabs. And for example, in USA, right, after 2020 itself, right, 600 billion, right, it's a rough estimate, has been already invested or is under investment, right, for different fabs, right, by different companies. And there are a lot of alliances and new, for example, India, right, is trying to do some kind of manufacturing, right, in back home. And then Middle East also interested in a lot of advanced things like data center, for example. And Europe also understanding okay, we has to be there. Japan also, Japan has a Rapidus consortium because like I mentioned in the 80s, they were the leaders. Now they're trying to come back, right? So there are a lot of alliances and experiments that are getting place at the moment. Okay, so let's touch upon what is going to happen right in future. Right now, the demand is huge, right, for chips, especially high efficient chips are very huge, but the supply is very less, right? Or it is it's really demanding, right? It's really demanding. There are a lot of use cases and I mean areas where you want to try new things, but the availability of chips, so it's very difficult. So just a pause here. So if you remember during COVID, we had a problem in availability of chips and cars were not getting produced, right? This is because let's say if you stop something not producing in TSMC fab or Samsung fab or Intel fab, it's going to stop the final product. So that's what it is happening. And lack of mature technology. So we are talking about 3 nanometers. So how much we can go down? 2 nanometer, 1 nanometer, it's very tough, right? Once you go down, you don't get that much efficiency on power and area. So people are thinking about new technologies like quantum computing. So we are talking about binary here, like right now, 0 and 1. But in the case of quantum, it will be qubits. Okay, it can store multiple states, but this is like early stage. And neuromorphic chips, like the entire architecture will be entirely different. The structure of the chip itself, right, is different. The way you think implement is different. It's like more like a human brain, you can say. But there are some practical implementation from Intel, for example, on this already. But these are also some of the newly going areas. So just wanted to highlight a few things before I close. So one thing I always want to reflect, right? So we can clearly see how amazingly the industry evolved, right, to a complex scientific problem, right? So it has a lot of basic science, a lot of problem yet to solve, right? It's not complete. We may think we achieved a lot of things, but there are a lot of complexities. And that's why the geopolitics is happening. That's the point. A lot of innovative designs like NVIDIA, for example, That's also a monopoly at the moment, right? So they initially designed for GPU and like graphics games, for example, but because of the AI use cases, they were able to quickly use the same architecture or upgrade, right, to support, right? And they also have a very good software ecosystem. Lot of AI research happening, and whatever research that we are implementing, if you want to put that as a on a final product, it has to come on a hardware, which is silicon, right? So that's why this is interconnected. And semiconductor and VLSI, right? At the moment, a lot of jobs, right? Still, we have a lot of jobs, a lot of innovation happening. It is controlling the economies, right? And one point I want to highlight at the moment, so we know a lot of things are being eaten up by AI. So there are things that are eaten up by AI in VLSI also, but not that easily replaceable, because it's very, as you can understand, we are talking about mass scale, lot of logic and different process and things like that. So early things, they are getting, many things are getting automated using AI or replaced by AI, but still there are a lot of things that you can't be replaced at the moment, okay, in codes at the moment by AI. So it is still a good area to pursue if you are thinking for a new generation or for your child or something like that. And we can clearly see that it is the geopolitical situation itself is shaped by the semiconductor industry trends. So it's a strategic industry shaping the future, inshallah. So yeah, so why we are talking about this, so just be aware about this. If you think about now, if you think about Muslim community, Muslim nations, and right, or what we have, right? We don't have anything in all this, right? That is a reality. Some of us are working in this industry, right? As employees, that's the only thing. And okay, maybe in Middle East some of the investments are coming there, but there are other reasons also for that. I don't know. I mean, I don't know from where we can start that discussion. We are very well behind on many things. But at least one point we can take, at least we should know what is happening, and then see, okay, where at least our next generation, our kids, right, can contribute, right, where they should focus or something like that, right? So at least that will help us at the moment. Otherwise, setting up a fad, it's like we are talking about running on billions, right, per month, right? So it's impossible at the moment, right? So, okay, inshallah, I just wanted to conclude here. We are almost maybe 45-50 minutes on the presentation. So yeah, would like to hear from all of you. And if there is anything that I can answer, if you have any questions, yeah, I'm happy to do that. Jazakallah khair.
Jazakallah, Abadaniya's excellent presentation, and I think it's a very eye-opening perspective on like you were mentioning in the end. We in the Muslim community usually think that oil, or we discuss about oil, we discuss about final products, we discuss about nuclear power and other things. But this is like the fundamental basic thing that is driving the technological innovations, economies, and whatever we see in our life, from healthcare to defense systems, now is being driven. And the picture that you gave about the time it takes to develop and the amount of research it takes is very enlightening, as well as a bit like soul searching on like how Muslims can go in this field. Yeah, Jazakallah khair. Anybody like any questions or any comments, reflections, please? Brother Umar.
Yeah, okay. Assalamu alaikum. Good to hear your presentation, Brother Nias. So basically, I just want to know this, all these microchips that are getting created, right? We have a lifetime even in our mobile phone that after some time we scrap it, right?
Yes.
Is there a possibility of reuse of those chips that are part of those mobiles?
Okay, it's a very vast question. So okay, there are multiple angles to that. So what happens, right, if you talk about the basic structures, right, finally it's a physical product. Once you put something on a silicon wafer, it's actually a physical product, right? So what happens is, as and when you use, it will have wear and tear, right? So let's say electrons are passing and it's hitting on the walls and things like that, right? So and that is one thing. Second thing is it will get heated up. There is also a lot of other weather related aspects and things like that. So eventually, let's say you started with your chip, right, is supporting, let's say, 3 gigahertz speed, right? Eventually, maybe another 5-10 years, it will come down, right, to that. So it's like aging, right? The same aging that happens to anything. So that is one thing. So it will happen, and only thing is the quality of the chip, right? So what happens right now is, let's say you got 5 years, right? You can compare like iPhone, for example. So iPhone chips, they are very good quality, right? Designs, and the final product is also very good because you can use it in, let's say, 5 years to 10 years, right? But there are chips from other companies, right, which are produced on a lower quality, right? And they will last for 1 or 2 years, right? Something like that. That is one part. Second thing, you can still use them. So it's like you got a, let's say, let me go back to this diagram, right? So